I'm calling this lecture 17. We've had a couple of cancellations due to Mountain Day, fall break, and whatnot. So what I want to do today is I want to talk about differentiating identities. This is one of my favorite techniques in all of mathematics. Okay? We proved on the second day of class the geometric series formula. Okay? It was a fun proof. You know, we got to play basketball. Right? It is hard work, and not just because it's difficult to shoot a basket, to prove an identity in mathematics. These are our bread and butter. Any time you can come up with a method that will generate new equalities from old, this is a good thing. So the whole point of differentiating identity is to actually create infinitely many new equalities from one equality. And it turns out that not only will we be creating new equalities, we'll be creating useful ones for probability. These will allow us to understand a variety of problems. So this will be a good way to introduce a couple of different distributions, talk a little bit about them, calculate their main quantities. Most of you are no longer freshmen, so you're no longer playing the freshman game where you meet someone and I think there's 5 standard questions you're supposed to ask, right?
Oh, yeah.
What are the standard questions you ask when you meet a frosh?
What's your entry?
What's your entry?
Where are you from?
Where you from? Have you declared a MathStats major yet? Like, what's your name?
Yeah. Yeah, no.
No.
Organically.
Your name comes up organically. Okay? But there's a couple of standard questions that you just ask, and most of you would agree on at least 3 of the 5 questions. And we can have some arguments as to the other ones. When you see a probability distribution, what do you ask that probability distribution? Yes? What's your mean? What's your variance? Right? Are you continuous or discrete? Usually that's pretty obvious, right? But if you actually have something that's fine enough mesh, a discrete distribution could look continuous and could be well approximated. So what we want to do is whenever we see a distribution, we want to calculate its mean, we want to calculate its variance. And so I'm going to show you a good way to do this with something called differentiating identities. So differentiating identities. What class do you think would be really useful right now? Nope, not calc, not DiffIdPrizeProblem. DiffIdPrizeProblem is a good guess based on what's written. When I taught multivariable calculus, the default was always linear algebra. In this class, what's the default? Real analysis. When in doubt, if I'm asking you what class, say real analysis, and you will be right about 90% of the time. Right? Real analysis will allow you to justify various things. So for example, actually this is kind of fun. For example, I can just write it like this. And that's the sum n goes from 0 to infinity of x to the n over n factorial. So you've hopefully talked about series expansions. If we differentiate, we can apply the operator d by dx to both sides. If we can say the derivative of the infinite sum is the same as the sum of the derivatives, then what we'll see is when we do this, we'll just get the sum, n goes from 1 to infinity, of n x to the n minus 1 over n times n minus 1 factorial. I'm just deliberately writing it out a long way. I don't have to include the n equals 0 term because that's just a constant. And when I take the derivative, I'm writing n factorial as n times n minus 1 in anticipation of the cancellation that's about to happen. The n's cancel, and I have a sum from 1 to infinity of x to the n minus 1 over n minus 1 factorial. So if you've actually taken a class in differential equations, you might have looked at series expansions. I just want to change my index of summation. If I just let m equal n minus 1, then this just reindexes to x to the m over m factorial. Well, what function is x to the m over m factorial if I sum from 0 to infinity? Yes? Yeah, this is just e to the x. So if we are allowed to say the derivative of a sum is the sum of the derivatives, then here is a proof that the derivative of e to the x is e to the x. Real analysis justifies this. It tells you when you are allowed to switch orders. You are not always allowed to switch orders. There are examples where this does not hold. But if this is true, then we get that this is e to the x. It feeds back and gives us this. Okay? So this is the difficulty, is justifying when we can switch. We talked about grouping things with parentheses. If you know the derivative of a sum is the sum of the derivatives, for two functions, we could then do 3 by saying f plus g plus h, we view it like this. And then the derivative of that would be f plus g prime plus h prime, which would then be f prime plus g prime plus h prime. And then we can just drop the parentheses because it's addition. And this is proof by grouping. Okay? This only works for finite sums. We do not know that the sum, that an infinite sum, we can differentiate term by term. We hope we can, but we don't know that we can. Okay? So now let's consider the geometric series formula. So the sum, and it goes from 0 to infinity, of x to the n is 1 over 1 minus x. Is that correct? Yes?
That is less than 1.
Almost.
Less than, or in between 0 and 1. Negative 1 and 1.
We could actually do a little bit better. And what letter did you say? What letter did you say is less than 1?
N.
Not n.
Oh, X.
X. And we need x to be less than 1 in absolute value. So this actually works even if x is complex, which we're not really studying right now, but we could do complex x as well. You always want to state the conditions on when this is valid. Imagine we could interchange the derivative and the sum. Is it hard to differentiate 1 over 1 minus x? No. And so we could actually use this to get a new formula. So let's apply the operator x d by dx. So what this means is I first take the derivative, and then I multiply by x. Why would I want to multiply by x? So what's the advantage of multiplying by x after I take the derivative? Yes? Yeah, I don't have to change my indices. It keeps the power of x over here, the Taylor series, as n. It's all about combinatorics. It's all about what is the easiest way to attack the mathematics to do the resulting algebra. I have reached the point where I am definitely more than I have been doing this class as long as most of you have been alive. Okay? When you have that many years of experience, you have a good sense of how to approach the problems and how to line it up so that the algebra won't be so bad. If you haven't spent the last 20 years of your life doing these derivatives, well, okay, you've got something to work on now for the next 20 years, but what you can always do is try looking at both. Try applying this, and also try applying just d by dx, and see which one is easier. Depending on what you want to look at, sometimes one is easier than the other. If I want to apply a derivative operator twice, this is getting painful. Because now when I apply x d by dx again, when I apply that once here, I'm now going to have a product, because I'll have an x times the derivative of that. If I only apply this, it's easier to apply more copies of this operator. But then I don't quite get powers of n on the other side. All right, so let's see what would happen. So assuming the derivative of the sum is the sum of the derivatives, the left-hand side becomes just the sum, and goes from 0 to infinity of n x to the n. And I don't have to really worry about whether or not I keep the n equals 0 term, because when n equals 0, this is just 0. On the right-hand side, when I apply x d by dx, I have 1 minus x to the negative 1. So when I take the derivative, I'll get negative 1, 1 minus x to the negative 2, and then the derivative of 1 minus x, which is negative 1, the negatives cancel, we multiply by x, and we get x over 1 minus x squared. And this will still be true if the absolute value of x is less than 1. So this is how the method of differentiating identities works. Okay? It is beautiful, it's incredible. We will see how this solves so many problems in probability. The difficulty is justifying this. Why is this such a hard statement to justify? What's the danger? Yes?
You've got an infinite sum resolution.
Yeah, we have an infinite sum. And so whenever you see an infinity in mathematics, that's a danger sign. So what could I do to avoid the danger? Yes?
Make sure that whatever's in your sum is a nice function that you can differentiate.
Well, but I still would have to deal with infinities. So what can I do to make sure I don't have to deal with infinities? Yes? Take a limit. Try dealing with things that are finite. So consider the sum, n goes from 0 to big N of x to the n. We know what this is, right? This is a finite geometric series. It's going to be 1 minus x to the n plus 1 over 1 minus x. I'm not going to go through too much detail here. I'm just going to put out a mathematical teaser. And if you're interested, try to make this rigorous, see what you can do with this. If we apply x d by dx to both sides, we will get the sum, n goes from 0 to n, of n x to the n is equal to x times the derivative of the above. I'll just do it like this. Okay? If I take x equals 1, what do I get over here? What does that give us? What would the left-hand side be if x equals 1? Tell me what I'd be adding. Oh, so that's actually the value. I'm adding 0 plus 1 plus 2 plus n. If I take the limit as x goes to 1, the hope is that this will actually give us the formula for the sum of the first 10 integers. So I'm a little bit worried because I've got a 1 minus x, so when I use the quotient rule, which we all remember and love so much, we'll have a 1 minus x squared down below. How do you think we're going to have to evaluate what happens? We're going to have a 0 over 0 as x goes to 1. What do you think we're going to have to use? L'Hopital. So as a really nice exercise, you can use L'Hopital, send x to 1, and you will actually get a formula for the sum of the first integers. What if you wanted a sum of the first integers squared? 1 squared plus 2 squared plus 3 squared. Apply it again. I might have actually included this in the book. Doing it 3 times was just, the algebra was so bad even I gave up. I could not motivate myself to do it. But here is a way to find a formula for the sum of the first n cubes or 4th powers or 5th powers. It's completely deterministic. There's no guessing. There's no trying to figure out, well, what is the formula? And now let me run mathematical induction. It's completely prescribed. So I'm hoping this gives you some sense of the power of the method of differentiating identities. All right? So we now actually have a formula for the sum of n x to the n. You should look at this as a way to calculate probabilities. And so what I want to talk about now is geometric random variables. There are a lot of different ways of defining some of the distributions we're looking at. This is very similar to the mathematicians and the physicists speaking slightly different languages at times. If you look at their choices for multinomial calculus, they don't quite align. Different people have different normalizations. What is the fountain of all knowledge? Wikipedia. So if you go to Wikipedia, they will often say these are the 2 different, or the 2 most common normalizations for the exponential random variable, or the geometric random variable. So what we can be doing is we can be thinking about things slightly different ways. Let's imagine we have a coin, and we keep tossing the coin until we get a success, until we get a hen. And we might want to know how long on average do we have to wait before we get our first hen. So we have fair coin, and let's say probability P of head tosses are independent, X is the number of tosses until the first head. And this is often viewed as the first success. If instead of having the first head, if we want to calculate the probability of getting the, how long we have to wait till we get 2 heads, do you think we could do that? 3 heads. So it's going to be very similar logic. And there are distributions that have names for stuff like this. Right now, I'm only going to look over here. So this is called a geometric random variable with parameter p. And I'm using p for success. Other people will use p for failure. So can someone tell me, what are the possible values that x takes on? Where does x live? What are the possible outputs for how many tosses it takes?
It's between 1 and infinity.
It's between 1 and infinity. I don't know how good you are at tossing coins, but I'm pretty sure you need at least 1 toss to get ahead. I have not watched The Simpsons in years. Did anybody see the recent episode where they were having fun with Boston? I looked up some of the lines. I think my favorite was, one of the Patriots fans, responding to allegations of us cheating. We don't cheat. We've won those 12 division titles in the last 10 years, fair and square. So you got to think a little bit before you do any calculation. What are the possible outputs? So here the possible outputs are 1, 2, ... infinity. Do you want that, or would you rather have 0? Another way of looking at it could be, how many failures do you have before the first success? And if you did the number of failures before the first success, then the outputs would be 0, 1, 2, 3, because it's possible you never failed. So depending on how you want to do things, there are slight differences. Doesn't make much of a difference which way you go, but you just have to be aware of this. All right, so let's calculate what's the probability that x equals n, that we get our first success on toss n. What would that be? Somebody who hasn't spoken yet. What's the probability that our first head is on toss n? Yes.
1 minus p, n minus 1 times p.
Excellent. So we had n minus 1 failures, and then we had a success. So the first thing we would want to do is we would want to check, is everything non-negative? Yes. Does it sum to 1? So we would have the sum, n goes from 1 to infinity, of 1 minus p to the n minus 1 times p. Well, since the sum is going from 1 to infinity, I can shift the index of summation down by 1. And I can pull out the p, and this is the same as p times the sum, n goes from 0 to infinity of 1 minus p to the n. What kind of series is this? Geometric, right? Probably where the name geometric random variable is coming from, right? Bless you. This would then just be p times 1 over 1 minus 1 minus p. And what's 1 minus 1 minus p? That's just p. Not less than 1. So if p equals 0, what would be going on? Yes.
We would never get ahead.
We would never get ahead.
So it would be, or we would have infinite tosses until we get ahead.
Right. So when we're doing this, I'm implicitly assuming that I'm not giving you the Mobius coin, which is always tails. Okay? You just have to be a little bit careful, because over here, it looks like this is fine for all values of p. We do need to assume that p is not 0. You really have to be careful to make sure. This is a probability distribution. So is there a smart ass here today? Anybody willing to be a smart ass? All right. Can you give me a lower bound for the mean? Really obvious, easy lower bound. 0. Right? Why is 0 a lower bound for the mean?
Because you're saying that p can equal 0 then.
Well, p can't be 0. Why is 0 a lower bound for the mean?
Because you don't toss the coin at all.
I'm sorry?
You don't toss the
Well,
coin.
but we're tossing the coin, and I want to know a lower bound. So 0 is a fine answer. You can actually do a slightly smarter, smart-ass answer than 0. Yes, 1. Why would 1 be a lower bound for the mean? You have to throw the coin at least once. If you look at the outputs are from 1 to infinity, right? We've got to have at least one toss. What do you think happens to the mean as p gets larger? As p increases, what do you think happens to the expected value of x? So p is the probability of a success. Do you think it's going to take you more tosses or fewer tosses to get ahead? Fewer. So before we even do any calculation, we have a rough sense of what's going on. The answer should be at least 1, and as p gets very large, the probability should be getting very close to 1. And it should be getting smaller the more we toss. It's nice to have a rough sense of the answer before you do the calculation. So let's calculate the expected value. So the expected value of x is going to be the sum, n goes from 1 to infinity, of n times the probability that x equals n. This is our formula for expected value. You take each outcome and you weigh it by how often it happens. All right? This is going to be the same as the sum, n goes from 1 to infinity. We'll have n, 1 minus p to the n minus 1 times p. Okay. Now we're at the point where there's lots of ways of doing the algebra. So I can think of 2 possible ways to do the algebra. Okay. One way to do the algebra is I can write n as n minus 1 plus 1. And if I write it like that, now the n minus 1 perfectly matches the exponent here. And then the 1, well, when the 1 hits that, that's just our probability distribution, which would sum to 1. So that's one way to do it. Okay? The other way to do it is I can multiply by 1 minus p over 1 minus p. And if I do that, now I fix the exponent there, and I make the exponent there n. Either way is fine. I think one way is finer than another. I think this way is a little bit cleaner. I don't have 2 sums that I'm now doing. I don't have to play index shifting games. But you really want to get a sense of how can I approach the algebra, how can I make it easier. So I'm going to go with this approach. And so what we would then get is that this would be equal to, I would pull out a p over 1 minus p, and I would have a sum, n goes from 1 to infinity of n, 1 minus p to the n. Do I have to start the sum at 1? Where could I start the sum if I so desire? 0. It's not going to change anything. And now, right about here on the board, we have the formula for the sum of n x to the n. So we showed that the sum of n x to the n goes from 0 to infinity, was equal to x over 1 minus x squared. If I dropped the square when I wrote it on the board, I apologize. We should have had a square when we took the derivative. So we just now substitute in. This is just going to be p over 1 minus p. And now here, what is our x? What's our x now? 1 minus p. So we get 1 minus p over 1 minus 1 over p, which would just be p squared. Okay? And now all the algebra we've done all these years ago helps. We cancel those, and we get, oh, beautiful, 1 over p. That's a nice answer. If the largest this can be is when p is small. Well, that makes sense. The smaller p is, the less likely you are to get ahead, and the more tosses you're going to need. As p is increasing, the mean is decreasing. Great. And the smallest this is going to be is if you use the Mobius coin, which is always ahead. which would be p equals 1, would be 1 toss. So we've just calculated the mean of a geometric random variable with parameter p is 1 over p. If we wanted to calculate the variance, we could calculate the variance. So the variance of a random variable x, there's a lot of ways to do this. One is it's going to be the sum of n minus the expected value of x squared times the probability x equals n. Another formula which we haven't put in class, it's in the book, I urge you to read that, is the variance of x. It's the expected value of x minus the expected value of x squared. And it turns out after you do some simplifications, and you really want to remember this formula, it's the expected value of the square of x. Yeah. It's the expected value of x squared minus the square of the expected value of x. This is a really good lemma to know. It's a really good, easy way to calculate the variance of a quantity. We've just calculated the mean of x. It's 1 over p. So if we wanted to calculate the second moment, all we have to do is replace n with n squared. How do we do that? We differentiate the identity again. So you would apply x d by dx again to the geometric series. Okay? Names are supposed to be good. This is named the geometric random variable, similar to the geometric series. You can see them all tied together. Okay. Any questions on this? So there's a whole slew of examples we can do. I'll do another one or two. I want to leave time to do a crackerjack problem. So let's do a binomial random variable. And so there's a huge number of distributions in the book. If you're going to stay in statistics, you really want to memorize them. So let's do a binomial with parameters p and n. So what this means is the probability that x equals k is going to be n choose k, p to the k, 1 minus p to the n minus k, if k is in 0 to n, and 0 otherwise. The way you should view a binomial random variable like this is I'm tossing a coin with probability p of heads n times, and I want to count how many heads do we get. Okay? It's called a binomial random variable. Do you know any theorems that seem to have the same word? Binomial theorem, right? Probably will be useful here. Step 1 in differentiating an identity. What do you need for step 1? Yes? You need an identity, right? This is not a very subtle subject, right? You need an identity. We have a binomial random variable. What do I know that help? Maybe the binomial theorem will be useful. So we could start off with x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. Binomial theorem. Now, let's apply x d by dx to both sides. Oh crap, should we take real analysis and justify interchanging the derivative and the sum? Why not? It's finite. Right? It's a finite sum. We can interchange a finite sum and a derivative without any trouble. So if I take the derivative on this side, I'll get x times n, x plus y to the n minus 1, and then the derivative of the inside with respect to x is just 1. And now on this side, I'll get the sum, k goes from 0 to n, of k, n choose k, x to the k, y to the n minus k. If I want to calculate the mean, what should I take for x? What should I take for y? So to find the mean, what should I take for x? What should I take for y? Yeah, x should be p, and y should be 1 minus p. It is extremely important when we do things. I do not want to be taking p and 1 minus p over here. Because if I do that, well, what's p plus 1 minus p? That's 1. The derivative on this side would be 0. And now over here, when I take derivatives, oh, good God, I would have a p and a 1 minus p. I'd have to deal with both of them. You need to hold off on when you set x equal to p, y to 1 minus p. You first take the identity, you take the derivative with respect to x, then you set things. And when we do this, we'll now get the expected value of x, which by definition is the sum, k goes from 0 to n of k, n choose k, p to the k, 1 minus p to the n minus k. Well, if we take x equal to p and y equal to 1 minus p, this quantity here is just 1 to the n minus 1. We just get n times p. And that is the mean of a binomial random variable. It's also hopefully reasonable. I'm flipping a coin n times. Each coin has probability p of being heads. How many heads do we expect? P times n. So it's a very good, reasonable answer. If you wanted to calculate the variance, you would now want to calculate the sum of k squared and choose k. We can do that. Okay? What's the easiest value of n to understand? 1, right? If n equals 1, we're just tossing a coin once. So another way of looking at this is this random variable x, we can write it as a sum of smaller random variables, where this is the outcome of the ith toss. So xi would be Bernoulli with probability p. And so if we flip a fair coin, the probability that a fair coin is heads is just p. What we're seeing here is if x is the sum of these processes, the expected value of the sum is the sum of the expected values. This is one of my favorite theorems in probability. Okay. Theorem. The expected value of x1 plus xn is the sum of the expected values. Okay. The expected value of a sum is the sum of the expected values. What this is telling us is that for some complicated things, we can reduce a difficult system to a bunch of simpler systems and understand how they piece together. Unfortunately, we do not have the variance of a sum is the sum of the variances. We do not have that. And so how things spread out is much harder than where they concentrate. This is one of the reasons why people often just calculate the mean of something that they're looking at, because the mean is a lot easier to do. Okay? And so we will prove this later. The proof is not too bad, but for now I'm going to just use this, that the expected value of a sum is the sum of the expected values. I'm going to use it to solve an extremely important problem. Last year, when I gave this lecture, it was right after coming back from a conference in Maine. Since my wife had a conference in another part of the country, my kids actually had to go. They actually had fun. They think that a math conference means you eat junk food, watch movies, and occasionally talk for a few minutes about math. We ate at a lot of McDonald's. The students I was driving were very good about this. We got 6 Happy Meal toys over 2 or 3 days. Of those 6 toys, there were, I think, 6 possibilities for each toy. Okay? What do you think the kids want? They want one of each. We got the same monster 4 freaking times out of 6. It was so bad we actually talked to a manager and said, come on, look, here's the receipts, because I have to itemize everything. You know, this is ridiculous. Can you please give us something else? Do you think McDonald's is choosing the toys with equal probabilities?
No.
No! Why not?
Some are cheaper to make than others.
No, it's not cheaper.
Because we want people to want
They want people to want, well, they don't, yeah. Whether or not people
It's like
want,
those-
they want people to tell their mummies and daddies and whoever has money, please take me to McDonald's, I just need one more toy. So how the toys, the probabilities are actually distributed is a really interesting marketing business question. Okay? So let's assume for simplicity that all toys are equally likely. This is often called the crackerjack problem. You have a box of crackerjacks and it has a toy inside. How many boxes do you need to open on average before you have one of each toy? Okay? So let's say there are C choices. 1, 2, all equally likely. And then each box, only one. You never have a box that has 2 toys. Okay? How many boxes do you think you need to open? I want a smart-ass answer.
C.
C. Okay? You need at least C boxes. Right? The C toys, you're not going to do it in fewer than C boxes. Anybody want to hazard an upper bound? You don't have to prove it, but what do you think a reasonable upper bound is? This is harder.
Maybe like C squared?
Yeah. Upper bound, probably C squared. Because it takes you most C boxes on average to get the first prize, then another C to get the second, then another C to get the third. Oh my God, I'm being quite stupid. If it took me C boxes to get the first prize, and if it took me then C more boxes to get the second, I should be getting other prizes that I haven't seen before. So I don't think they're going to be all failures. So probably somewhere between C and C squared. Anybody want to hazard what the actual answer is? Where you think it is between C and C squared? Do you think it's going to be as high as C squared, or do you think it's going to be a lot closer to C?
Close to C.
Probably closer to C. On problems like this, it's actually not bad just throwing like a log. And so the answer is going to be on the order of C log n, or I'm sorry, C log C. We actually know enough to solve this. The hard part is viewing the problem the right way. So we're going to let xk equal the expected wait time from having k minus 1 prizes or toys to having k. So the total wait time would be how long I have to wait to my first. Well, I guess it's just not expected. I guess it would be just the wait time. So not expected. It would be the wait time. So it's how long I have to wait for my first prize, plus how long I have to wait for my second prize, plus how long I have to wait for my last prize. If you guys determine one of the x's, I'll do the remaining C minus 1. Can anybody determine any of the
X1 equals 1?
x1 equals 1, right? McDonald's will not have my kids cry. There will be a toy inside that Happy Meal. Right? We all agree that x1 is just going to be 1.
Yeah.
So then the question is, how long do we have to wait? What's the probability if we have k minus 1 prizes before we get the next prize? What kind of probability does this sound like? I'm sorry, I couldn't.
Geometric series.
The geometric series is going to come into play, but what kind of probability does it sound like? Conditional probability. Given that we have, you're trying to figure out how to attack some problems, look for keywords. We'll look for keywords. Look for keywords if it's written on a piece of paper. Listen for keywords if I'm speaking at the blackboard. If you hear words like given that we have, you should be thinking conditional probability. Not surprisingly, the distribution of x1 is going to be very easy to find. It's going to be very fast. It's going to be 1. Which of the random variables do you think is going to have the longest expected wait? The last one. Oh my God, I need that last damn prize. Because now you've got to get just 1. Even if I'm waiting for the last 2, I have 2 chances for success. So what is the probability we wait for n boxes for next prize, given we have k minus 1 prizes. Okay? So somebody said that this is a geometric. Seems a really good thing to say, especially given the fact that we started today with a geometric random variable. We would need to figure out, so it's geometric, what's the probability of success? So what's the probability we get a new prize?
C plus 1 minus k over c.
So c plus 1 over k minus c?
C plus 1 minus k
Oh,
over c.
c plus 1 minus k, okay. I'm going to rewrite that as c minus k minus 1 over c. This is how many prizes I can't take. These are the inaccessible prizes. This is the number of prizes that would be considered new. So the probability that my prize is new is just going to be that. So in the interest of space, I will define pk, and the colon means this is a definition, to be c minus k minus 1 over c. And what looked like a really painful problem is actually not so bad. So what's the expected value of xk? Well, we calculated that earlier today. It's just 1 over the probability of success. So we can now use the linearity of expectation. So there's lots of different ways you can do things. I forget last year if I proved linearity of expectation first and then did this, or if I'm doing it this way because I want to motivate why we should do this theoretical proof. Why is linearity of expectation so nice? This is a painful problem. You want a miserable hour or two of your life, try to write down all the different ways you would do it in exactly C boxes, in exactly C plus 1, in exactly C plus 2. There are ways to do this, and there are ways that are not as painful. I don't know of ways that are pleasant. Right? Now, using linearity of expectation, the expected value of x is the expected value of x1 plus the expected value of xc. So this is going to be, we take the reciprocals, it's going to be c over c minus k minus 1, and we're going to sum k goes from 1 to c. Alright, doing a little bit of algebra, this is the same as, I can pull out the c. When k equals 1, I get a 1 over c. When k equals 2, I get a 1 over c minus 1. When k equals c, I get a 1 over 1. So it's just 1 plus 1 half plus 1 third plus 1 fourth plus 1 over c. When you just expand out and see what the algebra is. This is the harmonic sum. And now we use the fact that the harmonic sum is approximately the log of the number of terms. You can do a little bit better. We actually have the log of number of terms, and then it's either plus or minus the Euler-Mascheroni constant. But for our purposes, let's just say it's log of the number of terms. And we get our answers, and I will now use the squiggles because it's now just approximate, is about c times log of c. So that tells you roughly how many boxes you need if each one is equally likely. If they're not all equally likely, it's much harder. Because the great simplification we were able to make is to say it doesn't matter which prizes we've received. All we need to know is how many are left that we need to get. So this is one of my favorite problems. It really highlights a lot of the techniques we're doing. We see writing a complicated random variable in terms of a sum of simpler ones. As a rule of thumb, I would much rather do a lot of easy problems than one hard problem. And just find ways to combine things. The mean of a sum is the sum of the means. We have a special geometric random variable. We know what the expected value of that is. Now, the next question you might want to ask is, okay, so this is the average value. What are the fluctuations? How often is it going to be as large as twice c log c? Or could it be as high as c log squared c? And then you would want to know something about the variance, about how it's spread out. That's going to be a little bit harder. Okay? There are a lot more different distributions you can look at. We have time, I think, for one more. Any questions on this? Okay. So, they're all done in great detail in the book. I'll also link to the lecture from last year, which does a couple more of these as well. Let's do a continuous one. Let's do an exponential. So we say x is exponential with parameter lambda. This means that the probability I take on the value of x is equal to e to the negative x divided by lambda 1 over lambda if x is greater than or equal to 0 and 0 otherwise. There are unfortunately other people who use different notation. Instead of doing x divided by lambda, they do x times lambda. So their lambda is essentially my 1 over lambda. I like to look at it this way. I like my exponentials to have unitless quantities. So if x is in meters, lambda, my parameter, should also be in meters. And this is a really good way to view and interpret what's going on. Okay. So now, let's try to calculate the expected value. So what's the first thing we need? First thing we need. What method do you think we're going to use? Differentiating identities. So what's the first thing we need? An identity. Well, the only identity I know is the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx. What does this equal? 1. And so if this equals 1, if I multiply both sides by lambda, so multiply identity by lambda. This now makes it a lot easier to differentiate. I now have a lambda on one side, and now I want to take the derivative of both sides. This is not quite my probability distribution, but everything will work out. All right, so now let's apply d by dx. No, we don't want to apply d by dx. That would be foolish. We can't apply d by dx. Thinking. Why can't we apply d by dx? Yes.
Infinity.
Not because of infinity. I'm sorry? It's a definite integral, so why can't I apply d by dx? We have no x, we've integrated out x. I can't be applying d by dx. What should I apply? d by d lambda. That's the parameter. You take the derivative with respect to the parameter. So now, assuming the integral of the derivative is the derivative of the integral, we would get the integral from 0 to infinity, and now when we apply the d by d lambda, we get e to the negative x over lambda. And now when we take the derivative of this with respect to lambda, we'll get negative x over lambda. And we take the derivative of that, we'll get a lambda to the minus 2. The minuses will cancel, and we'll get an x over lambda squared dx. All right, and what's the derivative of lambda with respect to lambda? 1. This is almost the definition of the mean. I would want to write x times the probability density function. I'm off by a factor of lambda in the denominator. Not a big deal. Multiply through, and it's x 1 over lambda e to the negative x over lambda dx equals lambda. And there's the mean. And so this would be the expected value of x. Okay? We could calculate the variance. The key thing to notice is we want to make sure that we have a 1 over lambda times this at the end of the day. We can do this for the normal distribution. We can do this for Poisson random variables. There's a whole slew of all these different ones that we can apply this to. So I'm going to stop this here in terms of the different distributions we're going to look at. If people want to see more, let me know. I'm happy to do that. I've also asked you to think about, do you want me to flip one class every week or two to have more time in class to just go through more examples, more problems. So let me know about that. This is the advantage. The classes are recorded from last year.